So, the next PN junction that I will describe is called photodiode, and the word photo comes from photons. So, it has to do something with light. Essentially, it is a detector for light. Any PN junction, you have this gap, and if you shine light on it, then it is possible under certain conditions that the light energy is absorbed by an electron in valence band, and then it is promoted to conduction band. So, light is absorbed and a whole electron pair is created. So, essentially you have a photodiode which has a valence band and conduction band, and then you shine light on this junction area. So, you do not shine light on bands, you shine light only on material. So, if this is that junction area, this is that depletion layer, and if light falls on this, okay, if light falls on this and the composition is such that this photon can get absorbed into this material, then what will happen? Then if this light energy h nu that is taken up by this electron here, and if this gap is smaller than this h nu, then there is a chance other conservation laws have to be satisfied, then there is a chance that this gets absorbed into this bond here, the bond is broken, and then the electron reaches here. So, this electron will go here and correspondingly a hole will be created. So, visible light, let us say it is 400 nanometer to 700 nanometer. You can calculate the photon energy corresponding to these. Photon energy corresponding to this visible light, and this energy will be hc over lambda 1240 eV_nm over say 400 nm. That will give me 3.1 electron volts, and then for 700 nanometers this 1240 over 700. So, that will be how much? 1.8, around 1.8 eV. Okay, so, this is for 700 nanometer and this is for 400 nanometer. So, the photon energy ranges between somewhere between 1.8 eV to 3.1 eV or 3.2 eV, like that. So, this is the range. So, if the band gap is less than this, and if other momentum conservation everything is satisfied, then yes, then there is a chance. So, photodetectors are made with this idea, or if it is to be used in this fashion, we call it photodetector, and then light has to reach this depletion region. So, that in fabricating that has to be taken care of. All this junction, if I showed you that rectifying diode is all blackish covered in that blackish things. So, light will not reach the depletion region. So, here it is constructed so that you have a transparent cap on this junction, so that light from outside can go and fall on this material. And then if you have say n type here, or let me say you have this n type here, p type here, and say light is coming from this side. So, if this width is large, and there is absorption, so the photon may not reach that junction area, the depletion region area. So, it has to reach here, then only this effect will be there. Okay. So, the width of this p region, width of this n region, width of the depletion region, all these things are to be optimized properly, so that light does go there and fall. And how it is used, this, okay, symbol, its symbol will be, we will have a normal diode and then two arrows. These two arrows represent that light is falling on this, so it is a photodiode. Okay? And this is used as a photodetector. This is used as a photodetector. And how do we use that? We take this diode and connect it to a circuit, and in that circuit you have some current, and the circuit is reversed bias. So, if this is P, this is N, then this is that negative terminal of your voltage, and then this side is positive terminal. So, it is in a reverse bias. So, in a reverse bias, normally you will have a current like this. Normally, if you have reverse bias, this is the characteristic. Okay? When no light falls, no absorption, no light absorption, zero intensity. Of course, if you are doing the experiment in a room, light will be there, otherwise you will not be able to do the experiment. So, that light, background light is also there. So, when I say no light means intentionally I do not put any light. If any light is there, it is a background. Okay? But even if there is no light, even then this reverse saturation current is always there in a diode, and that will be here. But for a photodiode, since it is made in such a way that any light falling will contribute to the current, and therefore, this graph that I am drawing here, this is assuming that it is only the contribution from that depletion layer, this minority carriers which are going, which are giving you that reverse current. So, that is this. What happens when I shine light on this? When I shine light on this and light thus reaches that this depletion region or close to the depletion region, what is called one diffusion length. So, if very close to this depletion region, if something happens, then things can diffuse there. So, in that area if light falls, it creates new electron hole pairs. All right. So, in principle there is some efficiency. So, if 1000 photons are falling, there is an efficiency, a factor. So, those many 100 photons may get absorbed there, and each photon which is absorbed gives rise to one electron hole pair. Okay. There may be some other ways of dissipating the energy, but finally there is some fraction. Okay. So, if you shine light of certain intensity, and certain intensity means certain energy falling per unit area, and that means certain number of photons depending on the wavelength, certain number of photons falling on that area, and therefore, certain number of electron holes being produced, extra electron holes being produced, and this is in reverse bias. So, any electron hole pair which is produced here, because of this reverse bias, you have a large field, and that field will drift both the kinds of ions there. So, the field is in this direction. So, if an electron hole pair is produced here, the hole is promptly swept in this direction, electron is promptly swept in this direction. And correspondingly, if the electron is going this way, the current is going this way, that is the reverse current. So, if there is no light, you have a usual minority carrier current or the thermal generation of electron hole pairs in the depletion layer that is contributing to the current, and then you put light and extra hole electron pair are there and they are contributing to the current. So, this reverse current will increase, and so the characteristic will be something like this. In this side, if you extend, it will be going this way, but we are interested in this reverse bias thing. So, this is with some intensity, right, some lux, say some lux, say x lux. Lux is the unit for measuring intensity. So it is like this. If you increase the intensity, what will happen? Your characteristic will become this. This 2x lux. This is 3x lux. So if the voltage is fixed, if this reverse bias voltage is fixed, you can see that the current is changing, and it is changing in proportion to the light intensity. If the current changes, drop on this resistance also changes, and all those things will happen. But even if it shifts slightly, doesn't matter. This is fairly horizontal. All this is fairly horizontal. And so you can use this to measure the intensity of light, or at least compare two intensities. Okay? If you just look at this current here, look at this reverse bias current here, and then shine light, then the reading of this current meter, what current is going through this, what reverse bias current is going through this, that will be an indicator of what intensity is falling here. So for example, suppose you are doing an optics experiment, a diffraction experiment. You remember single slit diffraction pattern? In single slit diffraction pattern, you have a slit and then you send a monochromatic coherent light, and then on the other side, if you put a screen, what you find is you have a bright spot here, then a dark spot, then bright spot on the two sides, and you plot the intensity. The equations say that intensity should be of this type. Variation of intensity is of this type. Now, if I want to measure the intensity here and the intensity here, what do I do? In principle, I can put a photodiode here and shift this photodiode in small steps in this direction. And every time I can measure this reverse bias current. The photodiode is connected to a battery, a resistance, ammeter and all that, whatever current meter. So every time you measure that current, and that current will be proportional to the intensity, and that is how you can check that it goes like this, where the maximum is. If you just look through naked eyes, what you see is just a bright spot, here. But where exactly that maximum is in that bright spot, photodetector can say that. Now, there are several, if you actually go and do this and you don't get the result, so there are many other things which you have to take care. For example, this is stray light. Okay, as I said, in the room you will have some background light, so that will affect. Then when it falls on photodiode, you have to check that it is rightly falling on that. So the orientation of this photodiode, if you shift from here to here and the orientation also changes, then also there could be a problem. Then photodiode can saturate, so that if the intensity is very high, then it is no more proportional. So that can also create problems. So all those experimental things are to be taken care of, but nevertheless you do have a system which can detect light and which can measure its intensity. So that is photodiode. How does it look like? How does a photodiode look like? Okay. So I have a photodiode in my hand. And you see how it looks like. It's just a transparent window, a small unit with two legs. It's a diode, so it should have two legs, one for the P side, one for the N side, and then you have this material, and you can see this pinkish thing. That small thing is photodiode, and you just connect them. Okay, the next PN junction that I am now describing is very popular nowadays all over the world, and that is light emitting diode, LED, right, LED, light emitting diode. So, you have all varieties of LED bulbs and LED torch and emergency light and everything in LED, and government is also popularizing this. It has greatly replaced our filament bulbs or normal mercury tube lights and like that, because it's very power efficient. It gives lot of light per watt of electricity consumed, and therefore it's environment friendly and it is cost effective and all those things. The basic unit of LED is just a PN junction, right, but that PN junction is such that the band gap is in visible region, so that if a current goes through it, if you have this PN junction, this is P side, this is N side as usual, and you connect it in a forward bias condition like this, so that you have a current in this. You have reduced the barrier, so the diffusion current has increased manifold, the usual PN junction theory, and because of this increased diffusion, these majority carriers diffuse through that depletion layer. If you have lots many holes here, they diffuse on this side, and the electrons, they diffuse on this side. So, you have minority carrier injection, if you remember, right. In forward bias condition, you have minority injection, carrier injection, and once they are here, they are now minority carriers. These are now minority carriers in this side, this is P side, and then when they drift, you have lots of holes here, and you will have every chance of hole electron recombination. There are a lot of electrons here, and therefore you will have chance of electron hole recombination. And if during this recombination the energy which is released, if it is released in the form of a photon, and if that energy is in the visible range, we just calculated your visible energy, visible light, the energy range for photon is something like 1.8 electron volt to 3.1 electron volt. So, if an electron and hole, if they recombine, if the electron falls from the conduction band to this valence band, and if this extra energy is released in the form of a photon, and if this band gap happens to be somewhere in this range, what you will find is light is emitted from here. So, the symbol of this LED is also, you have this normal symbol of PN junction and then two arrows showing that light is emitting. So, that is the symbol of light emitting diode. So, what are the requirements? The first is this band gap should be in the visible range. Okay. So, for red, this is the photon energy. So, band gap should be around this, and for blue the band gap should be around this. So, to start with, we had only invisible range, this red LEDs, then later on other LEDs were also they came in production, and very recently 3 years ago 2014, that Nobel Prize for physics went to those Japanese scientists for blue LED. And once blue LED construction was possible, then white LED construction was also possible, because various combinations of red, green, blue will give you all shades and you can have white. and then blue falling on some kind of a phosphor also emits yellow, which together with that blue in proper proportion, it gives something like bluish whitish light. So that white LEDs are now possible, and that plays a great role in making these LED bulbs and LED tube lights and all those things. Now, we had been talking in terms of silicon. So far most of the time I talked in terms of silicon, but LEDs are not formed from silicon p-n junction. The one obvious reason is for silicon the band gap is 1.12 eV around this, and this is not in visible range. So, even if there is a recombination, a photon is emitted, that will not be in the visible range. But more severe restriction comes from something else. If I have a silicon p-n junction, and if this is the energy gap, and I can calculate what should be the corresponding wavelength corresponding to this energy of photon, that wavelength will be once again 1240 eV Nm and divided by 1.12 eV. So, how much that will be? That will be somewhere around say 1100 nanometer. Infrared. So, does it mean that when I pass a current in a silicon p-n junction, I will get 1100 nanometer infrared radiation? It does not work out that way because of another physics. Let me give a brief introduction of that. When we show this valence band and conduction band, we only show the energies. These are the energies. Nothing in horizontal, nothing changes in the horizontal direction. In the vertical direction, yes, the energy is increasing. As I go vertically up, the energy is increasing. But if I go horizontally towards right, in this diagram, nothing increases or decreases. Okay? It is just energy. We are just showing energy. But in semiconductors, the energy, that electron energy, that depends on the momentum of that electron in that crystal. So, the momentum is written in terms of popularly in quantum mechanics, the momentum is written as h by 2 pi, that is h cross, and then k vector, this k vector. So, this is actually the you can just say it is momentum vector, okay, multiplied by h cross will give you the momentum, and energy depends on that. So, if you take that energy versus k, on the horizontal direction you show k and in the vertical direction you show the energy, then this band diagram will not look like that. If this is EV, this energy is EV and this energy is EC, the lowest conduction band energy is EC and the highest valence band energy is EV, then it could be something like this. It could be something like this. This is EC and this is EV, and now the horizontal also means something. K is increasing in this direction and energy is increasing in this direction. Now, if this is the case and if the electron is here at the bottom of this conduction band and it falls to this top of the valence band and a photon can be emitted. But silicon band diagram does not look like this. Silicon band diagram is little bit different, and how does it look like? Its shape is for silicon, the band diagrams, it looks like something like this. So, the bottom of the conduction band and the top of the valence band, that is, yes, it is 1.12 eV, but this minimum occurs as a different k and this minimum occurs at a different k. So, if the electron has to go from here to here, somewhere here, the momentum is also changed appreciably, and just a photon emission cannot respect that conservation of momentum, because momentum has to change this much, and therefore some kind of a crystal momentum transfer to the crystal, some vibrations of crystal, that has to be bring in. You have to bring that, and so this photon of this energy comes out, that will not do. You will have vibrations and energy will go in vibrations, and we call it non-radiative transition. And here it is radiative transition. Here the bottom of the conduction band and top of the valence band is occurring almost at the same k. So, only very small amount of momentum change is involved, and a photon emitting can take care largely of that momentum conservation as well as energy conservation. So, this is, you call it radiative transition. Radiation is emitted, a photon is emitted. Such semiconductors are called direct band gap semiconductor. And these kind of semiconductors are called indirect band gap semiconductors. For LEDs, you need direct band gap semiconductors, and the materials which are used are gallium arsenide, then gallium arsenide, and you can put phosphorus here in certain proportion. You can have gallium nitride, you can have indium somewhere coming in. These kind of semiconductors, you can play with proportions and in what fraction they have to mix and all those things. They will be direct band semiconductor, and with proper composition their band gap can be in this range. Their band gap can be in this visible range. So, they can, when current goes through them in forward bias condition, they can emit light. So, that is LED.